Hello, stats students. I hope you guys are having a wonderful day. Let's go over your Unit 11 exam review. All right. The mean weekly earnings of a sample of 30 construction workers was $759 with a standard deviation of 73, and the mean weekly earnings of a sample of 28 manufacturing workers was $658 with a standard deviation of 65. Do construction workers and manufacturing workers have different weekly earnings? Use significance level of 0.1. Okay, this is numeric data because we have sample means, right? Sample means. We also have a standard deviation, so definitely numeric. Two samples because the sample sizes are different. We know they're not paired. And we do not know sigma because the standard deviation comes from the sample of 30 workers, not from the population. So we're dealing with a two-sample t-test here. So number one, we're going to define mu sub 1 as the mean weekly earnings of construction workers. And mu sub 2 as the mean weekly earnings of manufacturing workers. All right, so our null is that there is no difference. And our alternate is asking if there is a difference. So we're going to use not equal to. All right, let's check these conditions. So in step 4, we're going to check our conditions, and we've got construction, and we've got manufacturing, and we're going to check our conditions here. Condition A is it random? And it doesn't state, so we're going to assume for both. Part B, on this one, for normality for construction workers, 30 is not greater than 30, so this condition is not met. For manufacturing workers, 28, for normality, 28 is also not greater than 30, so this condition is not met either. Step C, 30 is less than 10% of the population. And step C, 28 is less than 10% of the population. And for D, for both, sigma is unknown. So not all conditions are met. So we need to proceed with caution. So all this means is that we realize that any outcome that we decide upon here may or may not be accurate because all of the conditions that ensure accuracy are not met, like B. Alpha equals 0.10. Okay, so we are doing a two-sample t-test. With our formula, t equals x bar 1 minus x bar 2 minus mu 1 minus mu 2 over the square root s sub 1 squared over n1 plus s sub 2 squared over n2. Step 7. All right, we are going to hit stat, tab over to test, and we're going down to option 4, two-sample t-test. Here we have the stats. We do not have the data, so we're going to use the stats. X bar sub 1 is going to be 759. S sub x1 is going to be 73. And n1 is 30. X sub 2 is 658. S sub x2 is 65. And n2 is 28. And we're dealing with a not equal to situation. Remember, pooled, just leave it as no and hit calculate. All right, so here's what we get. We get that t is equal to 5.572. Step 8, we read our probability statement. Remember, step 8 and step 3 need to match. Since this is a positive z-score, we're going to use a greater than symbol here. So it's 2 times the probability that t is greater than 5.572. And the p-value you should have gotten off is 7.500 times 10 to the negative, oops, I don't know why I put a greater than sign, times 10 to the negative 7th, okay, which is approximately 0. Remember, you need to have this notation here, 2 in the front, but the p-value you were given already takes this into account because we chose the not equal to calculation, okay? So approximately 0, which is less than alpha, so we reject the null. So with a p-value of approximately 0, the data suggests, yes, there is a difference. There is a difference in weekly earnings between construction and manufacturing workers. Sorry, I was running out of room. Okay, now the natural question is, well, how much of a difference? So find a 98% confidence interval for the true mean difference in weekly earnings. Okay, so you need to let everyone know that you need to check your conditions, but that we're not going to do it again, okay? So see conditions from part A. They have not changed. Proceed with caution. All right, and then the interval that follows is a 2 sample t interval. And here's the formula for that. It's x bar 1 minus x bar 2 plus or minus the critical value of t star times the square root s sub 1 squared over n1 plus s sub 2 squared over n2. Okay, so we're going to go to our calculator. We're going to hit stat, tab over to test, and we're going to go down to option 0, which is a 2 sample t interval. You should have all the information just carried over, and a confidence level of 0.98, pooled no, so we're going to calculate, and you should get 57.9, oops, 591, so I'm just going to put 59 because we're dealing with dollars here, and 144.41. Remember that you had construction workers first. So you had mu1 minus mu2, where mu1 is construction workers and mu2 is manufacturing workers. So since you got out a positive value here, we are knowing that the construction workers are making more than manufacturing workers. So we can say, hey, I want this erase. There we go. Right here. Let me write it in a different color since I'm running out of room here. I'm going to zoom in. We are 98% confident that the mean weekly earnings of construction workers is between $57.59 and $144.41 more than manufacturing workers. Okay? Nice. Explain how the confidence interval supports the test results. Okay, well, since the test reveals that there's a significant difference between construction workers and manufacturing workers, we're going to build a confidence interval to measure that difference, okay? So the test tells us, yes, there's a difference, and the confidence interval supports that, saying, okay, we know there's a difference, and the confidence interval gives us an idea of how much and to what percent we're confident that that's true. So we're 98% confident that based on of our sample that the true difference is between these two values. But remember that we are proceeding with caution because not all conditions are met. The sample sizes are a little small, so this may not be representative of the true difference of the population of those workers. Okay, so that was a brief verbal explanation that you guys can take what you want out of it and write that down. Okay, number 2, let's do this. In 1980, 750 randomly chosen men between the years of 20 and 34 years old. Sorry, it got noisy. Okay, so in 1980, of 750 randomly chosen men 20 to 34 years old, 130 were found to be overweight, whereas in 1990, 700 randomly chosen men 20 to 34 years old, 160 were found to be overweight. So the question is do the data provide sufficient evidence to conclude that men 20 to 34 years old have a higher percentage of overall weight in 1990 than 10 years earlier? This is a yes or a no question. There are 2 samples, therefore this is a 2 proportion z-test, okay? So let's look at our 2 proportions. Proportion 1 is equal to 130 out of 750, which is 0.17. And proportion 2 is equal to 160 out of 700, which is 0.23. Step 1, pi sub 1 is equal to the true proportion of men 20 to 34 years old, overweight in 1980. And pi sub 2 is the true proportion of men 20 to 34 years old, overweight in 1990. Okay. The null is that there's no difference, okay? And the alternate, let's go look at the question that's being asked, okay? It says, to conclude that men 20 to 34 years old have a higher percentage, were overweight in 1990 than 10 years earlier. So we're saying that proportion 1, 1980, is less than proportion 2, which is in 1990. Okay? Step 4, we're going to check our conditions. Okay, so we've got for 1980 and for 1990. Conditions for this sample is part 1, is it random? And yeah, it's stated for both. Okay, part B. N 130, oops, sorry, 750 n times p is 0.17. Well, that's equal to 130, and that is greater than or equal to 10. We know that because of our proportion above. So part C, 750 times 0.83, we can just do the simple subtraction in our head. We know it's going to be greater than or equal to 10 also. And D, 750 is less than 10% of the population. Okay, part B. N, which is 700, times P, which is 0.23, is equal to 160. So we know that's greater than or equal to 10. And so then we know just by, subtraction that the opposite is also going to be greater than or equal to 10. We can just kind of do that mentally. And 700 is less than 10% of the population, so we're good. We're good to go here. Step 5, it does tell me at the 5% significance level, so alpha is equal to 0.05. Step 6, we're doing a 2-prop z-test here, okay, 2-proportion z-test. So formula is very important. Z is equal to p sub 1 minus p sub 2 over the square root p sub c 1 minus p sub c over n1 plus p sub c 1 minus p sub c over n2. Eek. Squeeze that in. Step 7, we're going to hit stat on our calculator, tab over to test, and we're choosing option number 6, 2-prop z-test, okay? X bar 2-prop z-test. Okay, x sub 1 is 130. N sub 1 is 750. X sub 2 is 160. And N sub 2 is 700. We're looking at less than. Hit calculate. All right, so for step 7, you should get that z equals negative 2.628. Yes, 628. And so our probability statement should match step 3. The probability of z being less than negative 2.628 is equal to a p-value of 0.004, which is less than alpha. So we're going to reject the null. Step 9. With a p-value of approximately 0.4%, the data suggests that a higher percentage of men 20 to 34 years old were overweight. My pinky did that. In 1990 than 10 years earlier. Okay. Awesome. Part B, well, how much overweight we want to know. We're curious. So same thing, you're going to check your conditions. We're going to see conditions from part A. All were met, and nothing has changed. We're running a 2-prop z interval. Here's our formula, P1 minus P2 plus or minus a z star. Square root P1, 1 minus P1 over N1 plus P2, 1 minus P2 over N2. We're going to take our calculator, go to stat, tab over to tests. We're going down to option B, 2-prop z int. Everything should already be there for you. Just make sure you change your confidence level to 95% or 0.95 and hit calculate. And we should get negative 0.0965 and negative 0.014. Remember, we're looking at the first one being less than the second one, okay? So let's interpret this over here. Okay, we are 95% confident. Okay, because remember, if you say pi 1 is less than pi 2, that means pi 1 minus pi 2 is less than 0. So we're saying the first one, 1980, minus the second one, 1990, is going to be a negative value because this was less. So that's how we want to interpret it, okay? So we are 95% confident the true proportion of men 20 to 34 years old who are overweight was between 1.4% and 9.65% less in 1980 than 1990. Okay. I'm going to get rid of this because it's just scratch work and it's ugly. All right. Let's look at this last question. Many people have claimed that U.S. has more issues with overweight people. Does this data support this statement? I mean, yeah, I guess it does, because you're seeing the weight increase by between 1 to, a little bit less than 10% in 10 years. So this would suggest that weight would continue to increase in the future. Okay, so there's another little verbal explanation for you that you guys can take and make what you want out of it. One more test. Okay, so let's move on to the next one. 12 people with arachnophobia were asked to look at pictures of spiders and then look at real spiders. Their anxiety levels were recorded. The data is recorded below. Okay, we've got the data here. So this is definitely numeric. There's two samples and they're paired in a meaningful way because this is the same person, okay? So the same person looked at a picture in a reel, all of that. So this is definitely going to be a paired t-test, okay? You can do this. Let's just get going here. Okay, so number one, this is a paired t-test for sure. So mu sub d is going to be the true mean difference in anxiety level with the picture or real spider. Okay, so for me, I'm going to just do picture minus real. Remember, if you're subtracting, you need to tell me the way you're subtracting for paired data, okay? The null is that, there's going to be no difference. And the alternate, let's go look at what the question is asking. It just says, is there significantly a higher level of anxiety? So that means the real would produce more anxiety. So I would expect, if I had a bigger number for the real and a smaller number for the picture, I would expect subtraction this way to result a negative value. So I'd expect mu sub d to be less than 0. And if you switched this and you said real minus picture, then this will be greater than 0, okay? All right, so let's, number 4, check your conditions. Part A is the sample random? Let's see, it's going to be assumed. Okay, part B, normality. Okay, so what you have to do here is one of two things. You can either subtract and create a new list, or you can enter this data into list 1 and this data into list 2, subtract in list 3, list 1 minus list 2, and then that would be the list you're working with to make the normality plot. That's what I'm going to do. Remember, to create a normality plot, you hit second stat plot. On type, you choose the 6th option, this one, okay? And data orientation doesn't matter. I always say X, but you can do whatever one. Either one will show you if it's a straight line or not, okay? Hit graph and then hit zoom 9 so that you can see exactly where your data goes. For me, mine looks something like this. Okay, so normality plot is approximately linear, so data is approximately normal. Make sure you check that, because the day you don't is the day it's going to be all messed up and then you'll get in trouble. Okay, C, 12 is less than 10% of that population, and for D, sigma is unknown because we only have the sample data. Okay, let's do this. For step 5, alpha is going to be equal to, we don't have one, so 1 in doubt, 0.05. And step 6, I'm going to just squeeze it down here. This is a paired t-test. So here's our formula. T is equal to x bar sub d minus mu sub d over s sub d over the square root of n. Okay. All right. So for this, we're going to hit stat and we're going to tab over to test. We're just doing a regular t-test, except for we're using the data from the subtracted list, which is in list 3. So for this, you're going to select data. Mu sub 0 is equal to 0 since, oops, that's what we have right here. For me, my data is located in list 3. That's where I subtracted these 2 values. So make sure you choose the correct list. And we're looking at less than. I'm going to hit calculate. Let's see. You should get a t value for step 7 of t equaling negative 2.473. Negative 2.473. All right. Remember your sign in step 8 and 3 need to match. The probability of t being less than negative 2.473 is equal to that p-value right there of 0.015. Man, if we picked an alpha level of 0.01, this would have been a fail to reject, but we picked 0.05, so this is less than alpha, and we'll reject the null. So 9 with a p-value of 1.5%, the data suggests that there is a higher level of anxiety when looking at real spiders instead of a picture. I mean, duh. A real spider can jump on you. Yuck. All right, let's move on to C. Create a 98% confidence interval for the true difference. All right, I want to know how much more anxiety you're going to have. Okay, so check conditions. Remember, C conditions from part A. All were met and nothing has changed. Okay, this is a paired t interval. So we're looking at x bar sub d plus or minus t star s sub d over square root of n. Okay, so we're going to hit stat and we're going to run over to test and we're going to pick t interval, which is option 8. We already have the data in list 3, which is how it's paired. Okay, that's the part that makes it paired. Confidence level is 0.99. Make sure you change that. and calculate, you should get negative 15.79 to 1.7929. Okay, this is going to be a little difficult to interpret, but we can do it. So we are, remember, the reason this is negative is I have the picture minus the real. So we are 99% confident the true difference in anxiety level is between 15.79 less or 1.79 more when viewing a picture rather than a real spider. This is kind of a puzzling confidence interval because if you notice, 0 is included in the interval, which kind of makes it seem like no difference is a possibility, even though we ruled that out above. But the reason why that's kind of possible is, one, this p-value is close. If I would have chosen an alpha level of 0.01, then this would correspond to the thought that, yeah, okay, it's really close. However, if you notice the length of the interval, most of the values are negative. So this just kind of shows me that the possibility of no difference is close. If we would have made this confidence level less, we probably would not have included the difference of 0. But since we made it more, remember the interval opens up a little bit wider, which is why 0 is included. So a little like strange that this is happening, but just because of the compounded parameters that we set of alpha equaling 0.05 and of this high confidence level, 0 happens to fall in there, okay? So that's what's happening there. Let me erase this. Okay, and then the last part, sorry for a lengthy video, just like hopefully you fast forward it if you just, already know what's going on. Okay, for each description, decide what type of test or confidence interval would be used. Cool. Okay, here we go. Research question. Is there a difference in marks following a teaching intervention? Okay. The marks for a group of students before and after a teaching intervention are recorded. Okay, so this would probably be a sample. So there's that. And sigma would be unknown if this was a sample. The marks for a group of students before and after a teaching intervention are recorded. I wish I had a little more info so we could decide if it was Z or T, but I'm gonna go with T because this is definitely dependent since we have before and after. And I'm gonna say this group is not representative of all. Students, so that's why I'm gonna make it a paired t-test, okay? According to official census figures, 8% of couples living together are not married. A researcher took a random sample of 400 couples and found that 95% of them are not married. Test at the 15% significance level if the current percentage of unmarried couples is different from 8%. Okay, so let's check this out here. 8% of couples living together are not married. A researcher took a random sample of 400 couples and found that 9.5% of them are not married. All right, so basically all we have here is one sample, and this is a proportion. So, because we're saying you're married or you're not. So this has to be a 1 prop Z test. C, in a packing plant, a machine packs cartons with jars. It is supposed that a new machine will pack faster on the average than the machine currently used. To test that hypothesis, the time it takes each machine to pack 10 cartons are recorded. Yeah, so we're gonna have two samples here, okay? Two samples of 10, and it's really not paired in a meaningful way, okay? Because we're not having the same jar go through machine 1 and machine 2, and we're comparing it's two separate samples. And since it's only going to be a sample of 10, we're not going to have any population information. So it's not paired in a meaningful way, no population information, and the data is numeric because we're looking at the time it takes, and time is numeric. So this is definitely going to be a 2 sample t-test. All right. D. The Time magazine reported that the results of a telephone poll of 800 American adults. The question posed of the Americans who were surveyed was, should the federal tax on cigarettes be raised to pay for health reform? Okay, well, this is very small information, but should the federal tax on cigarettes be raised to pay for healthcare reform? This is a proportion, right? And we have 800 American adults, 1 sample. So this is also a 1 prop Z test. Okay. Possibly an interval if you want to find out how many people. But this has a very little amount of information. Okay. A psychologist claims that the mean age at which children start walking is 12.5 months. The following data give the age at which 18 randomly selected children started walking. Okay, so here's our raw data. So we know nothing about the population except for the population mean. We have 1 sample. That's it. So this would just be a t-test. Numeric data. Okay. The population standard deviation for waiting times to be seated at a restaurant is known to be 10 minutes. Cool. I know I'm dealing with Z of something. An expensive restaurant claims that the average waiting time for dinner is approximately 1 hour. Okay. Expensive, 1 hour. But we suspect this claim is inflated to make the restaurant appear more exclusive and successful. A random sample of 30 customers yielded a sample average waiting times of 50 minutes. 1 sample, numeric data, we know things about the population. This is going to be a Z test. Last one. The amount of a certain trace element in blood is known to vary with a standard deviation of 14.1 parts per million for male blood donors and 9.5 parts per million for female donors. Random samples of 75 males and 50 females yield concentration means of 28 and 33, respectively. What is the likelihood the population means of concentrations of the elements are the same for men and women? All right, we've got numeric data because it says, sample means. This tells me right here that they are meant to vary with a standard deviation of 4.1. This is population data, okay? That's for males and 9.5 for females. So I do know sigma. I have 2 random samples that are of different sizes, okay? So numeric data, we know sigma for both, and I have 2 sample sizes, so this has to be a 2 sample SATC test. All right, you guys, sorry for the lengthy video, but hopefully it helped. Have a great day. Office hours is today from 2 to 3 if you need any help. Oh, geez, stop it now. Oops.